Assalamu alaikum. This is the last lecture of properties of matter. In this last lecture, we are going to discuss elasticity. What is elasticity and its definition, and the force may produce change in size and shape of the object. Stress, strain, and Young modulus. We are going to define these three terms, and what is Hooke's law and what is the elastic limit in Hooke's law. So first we are going to discuss about elasticity. Elasticity, you can see this. This is your daily life observations. The things, when a force is applied, there is a change in shape, and when the force is removed, it comes back to its original configuration. Now, the elasticity, the body regains its original configuration, means length, shape, or volume, after you remove the deforming force. This is called elasticity, or we can say the ability of an object or material to resume its normal shape after being stretched or compressed. Means whenever the deforming force, you can see that this is the when the force is applied, there is a deformation in it, and when the force is removed, it's regained its original shape. So if an external force is applied to a material, it causes deformation in the molecular structure of the material, and if when we there is a increase in the intermolecular distance, and when we remove that force, because of the attractive force between the molecules, it regains its original shape, and this process is called elasticity of material. uh, in other words, the amount of compression means we can either apply the force just to elongate the material, or we can compress the material. Just like this, you can compress the spring, it will change its shape, but when the deforming force, this is the red arrows, they are removed, it return back to its original shape. So this is uh, called the elasticity, and we can say that this amount of stretching or compression, it is directly proportional to the applied force, but to a certain limit. The object regained its shape, but to a certain limit, if the applied force is more, uh, then it will change. It may change its shape. It may not come back to its original shape. So we see that you can say there is rubber band. This certain point is called elastic limit. In this rubber, if you compress them, it the shape changes, and but when the force applied is removed, it come back to its original shape. And but this will happen to a certain limit, and this limit is called elastic limit. Beyond this, the thing may not regain its shape. There is a change in shape, and we go further beyond it, it may break, or there may be a permanently distorted or D-shape, or maybe break. For instance, if this is a spring, if you apply the force, there is an elongation, and this elongation is in elastic limit. If you further apply the force, there is a change in the shape of the spring. If we keep on applying the force, ultimately the spring will break. So this is elasticity is the uh, it is the property of the ability of a material to regain its shape after the deforming force is removed, but it is to a certain limit. Now, what is perfectly elastic body? The perfectly elastic body regained its original configuration immediately and completely after the removal of the deforming force. Quartz, phosphorus, phosphor bronze are the example of nearly perfectly elastic bodies. Plasticity, when a body is unable to regain its original size and shape, even on the removal of the deforming force. If you stretch it beyond the elastic limit, so uh, the object start to deform, and it will not uh, come back to its original shape. Like your if you take an example of a spring, if you stretch it to a certain limit, it will come back to its original shape. But if that limit, if you stretch it beyond too much, so then the spring will lose its shape, and that lose of shape is called the plasticity. Now, stress is the restoring force per unit area perpendicular to the surface of the body. Uh, so whenever an force is applied, this force is applied in this material, a force is developed that is equal in magnitude to the applied force, so that whenever this applied force is removed, the thing come back to its original shape. So there are, so this is force, the restoring force per unit area, or we say that internal force applied due to the uh, internal force developed due to the applied force is called stress. So uh, they are always equal in magnitude. So it is the restoring force per unit area perpendicular to the surface of the body, and there are two types, tensile and compressive stress. It is a ratio of the restoring, yani that is the internal force developed due to the applied force produced when the substance is deformed to the area over which it is this force acts. In equilibrium, this force is equal in magnitude to the externally applied force. So, in other words, simply we can say that stress is defined as the force per unit area. It is given by the formula. You can see that this is the symbol of the stress. This rho, this is the stress applied. This is the force is applied, which is equal in magnitude to the restoring or internal force, and A is the area on which the stress is being applied. So this is what the stress is. Now, the SI unit of stress is force per unit area. The stress applied to a material can be of two types, may be tensile and may be compressive stress. It is now what is a tensile stress? It is the force applied per unit area which result in increase in length or area of a body. Object under tensile stress become thinner and longer. Compressive stress, it is a force applied per unit area which results in the decrease in length or area of a body. The object under compressive stress become thicker and shorter. Now, what is strain? It is the ratio of the change in length or shape to the original size and shape. It has no dimension, it is just a number. You can see that it is a ratio of two similar quantities. This only shows you this is a number. According to this, it is defined as the amount of deformation experienced by the body in the direction of applied force. So, divided by the initial dimension of the body, the relation can be mathematically written as this E epsilon, that is representing this is the strain, and delta is the change in length, and L is the original length. The strain is a dimensional quantity as it is just defined the relative change in shape. That is the elongation. Strain is the elongation delta L per unit original length. Depending on stress application, strain experiences in a body can be of two types. Tensile strain, it is the change in length of a body due to the application of tensile stress. Longitudinal strain, if the deforming force produces a change in length alone, the strain produced in the body is called longitudinal strain or tensile strain. Compressive strain, it is a change in length or area of our body due to the application of compressive strain. So, this is overall about it. Now, we say that stress is directly proportional to strain. So, there is a constant of proportionality between them that is called the Young modulus. Now, what is a Young modulus? If you imagine a piece of dough, stretch it, it gets longer and thinner. If you squash it, it gets shorter and fatter. Now imagine a piece of granite. Try the same experiment on this. The change in shape must surely occur, but to the our eye, that it is imperceptible. We cannot see that change. There may be a change, but we cannot see that. Some material is stretched and squashed quite easily. Just you can see, you have seen the above example, like rubber band has can be stretched. Spring can be stretched and compressed, and you can see that. But if the hard materials, rigid materials are they also compress and stretched, but that they stretch by a very little amount, and it is we cannot see that, we are unable to recognize, we cannot perceive that change. The quantity that describe a material response to the stress applied normal to the opposite faces is called Young modulus, and we call this Young modulus in honor of the English scientist. So uh, his name is Young's. So Young modulus is the constant of proportionality between stress and strain. The Young modulus of a material is given by the ratio of stress and strain according to the stress of the material. The relation given is y is equal to, this is stress upon strain. So stress is equal to F upon A, and strain is equal to change in length per unit original length. If we put that value, y is equal to F upon A, then we will get an equation for y in terms of original length, force and area. Y is equal to F upon A into L upon delta L. So this Young modulus may be can be represented by Y or E, and this is the SI unit of the Young modulus is Newton per meter square, and uh, with the value of the Young modulus for material, the rigidity of body can be determined. If you see a table of the Young modulus for the different material, because it is specific for each material have different value of the Young modulus, those material that expand very easily and their expansion and contraction can be seen with the eye, so that have a less value of the Young modulus, and those who are the harder subject materials, they have a more value for the Young modulus. The higher the value of the Young modulus, more rigid will be your material. So the mechanical property of your material to it is the mechanical property of a material to withstand the compression or elongation with respect to its length. So this is denoted by E or Y, and it is as the Young modulus is a mere of mechanical property of linear elastic solids like rods and wires. So, Young modelers, just tell me how much stress object can have. Now you can, we are go a numerical for it. A wire 2 meter long, that is the original length, 2 millimeter in diameter. That obviously wire is a circular shape cross section area, so the diameter is 2 meter, radius is the half of the diameter, it means 1 millimeter, and if we convert millimeter into meter, 1 into 10 power minus 3 meter. When stretched by a weight of 80 newtons, means 80 newton where weight is hanged in the wire, so it is a 2 meter long wire stretches by 2 millimeter only. Length sorry, a 2 meter long wire having the diameter 2 millimeter is stretched by 0.24 millimeters. It means that the delta L in this case is given as that is the increase in length, that is delta L is given as 0.24 millimeter. Again converting millimeter into meter, 0.24 into 10 power minus 3 meter. What we have to find is stress, we have to find stress, we have to find strain, and we have to find the Young modulus of the material. Now formula for stress is force per unit area, that is the internal force or resisting restoring force per unit area. Strain is change in length upon the original length. Young modulus is equal to stress by strain. So first our objective is I'm going to find stress. Stress is force per unit area. Force is given as 80 newtons, and area, we know that it is the area of cross section of a wire is circular, so area of a circle is pi r square. So pi is 3.14, r is, we have already calculated, 1 into 10 power minus 3 and square. So by after calculating them we will get stress is 2.54 into 10 power 7 newton per meter square. Now strain is equal to change in length upon original length. So change in length is given by 0.24 into 10 power minus 3 meters divided by original length, that is 2 meters. So the strain comes out to be 0.12 into 10 power minus 3, and this is, it is just a number, it is just the ratio of the two similar quantities. Now, Young modulus is equal to stress upon strain. Stress value is 2.54 into 10 power 7, and strain is 0.12 into 10 power minus 3. So, the Young modulus will be 2.11 into 10 power 11 by calculation. Now, the constant Young modulus applies to the linear elastic substances. So this is the stress and strain curve of those substances. There are different points on it. The first point is proportionality limit, elastic limit, yield point, ultimate stress point, fracture or breaking point. So from 0 to A, we can say this obeys the Hooke's law, means that the stress is directly proportional to a strain, and we will get a almost a straight line in this case, because this is the uh, limit in which the Hooke's law is applied. A to B is again a yield point, that it means that if we further elongate it, there is a change, the deformation start to occur, and there is a lower yield point too, so that at this point the region, at this region, the deforming, at this point the things return to its original shape, but after B, that BC point, the things do not return to its original shape. This is the plastic region and the deformation. For instance, if the spring is stretched beyond B, the spring will not be returned to its original position, but there is a deformation in that. Okay, now then if we further uh, uh, go apply this, applied force is applied, there is a point, this is the last point, that uh, after which the breaking or the fracture occurs. This is the last limit, is the breaking stress. So after this, if we apply more, then there is a fracture, or the, of suppose if it is a spring or a wire, it will break at this point. So these are the explanation of the different points on it. The proportionality limit, region in which strain curve obeys Hooke's law. Elastic limit, point on the graph to which, up to which the material returns to its original position when the load or the force acting on it is removed. Yield point is defined as the point at which material start to deform plastically, means that it will not, uh, after the yield point, permanent plastic deformation occur. It means that there is when the thing material enters in the plastic region, there is no chance that it will return back to its original shape. Ultimate stress point, this is the maximum stress a material can endure before failure, means that before breaking, or after this the breaking occurs, the spring or wire or anything that breaks down. So what is Hooke's law? Hooke's law states that stress is directly proportional to strain within the elastic limit, and the ratio of stress and strain produced is a constant, and that constant is called the modulus of elasticity. So you can see this is the extent force and extension graph. You can see up till this point, this is called the limit of operationality. The material obeys the Hooke's law, and after this, it enters the plastic region and do not obey. Now you can see that if this is the spring, unstretched spring, if force is applied to it, it will there is an extension in the string, it will extend, and if this force is double, this extension also doubles. So we say that stress is directly proportional to strain up to, but this will be up to a certain limit. So up to a certain limit that it obeys the Hooke's law, that stress is directly proportional to the strain. Now you can see that video for this.
Hooke's law is valid only up to a certain limit, and only for small stresses. But how do we find that? And more importantly, what happens beyond that point if I increase the stress beyond that point? See, we also know that at some point, if I increase the stress too much, a body will break, right? We have seen stuff breaking. So how does all this happen? To analyze this, let's do a simple exercise. So let's take, let's say, a metallic wire like this, and plot the stress versus strain graph. So we'll apply a stress, see, observe the strain, and plot a graph with the stress on the y-axis and the strain on the x-axis. Okay, so let's do that. So this is our normal length of the wire. So the first thing I'm going to do is I'm going to start applying a slow stress. Like slowly, I'm going to increase the length. So obviously, we know that as I keep increasing the stress, from Hooke's law, we know that the strain will also increase. So therefore, basically, as I keep increasing F, or the force, the elongation will keep increasing, right? And we find that if you draw the graph, it will be proportional. So therefore, it will be a straight line. It will increase like this. And the slope of this graph will be equal to y, which is the Young's modulus. Okay, all that is fine. Also, if I stop in between, and if I bring it back slowly, that is, if I reduce the force slowly, and I let go, at the end, it will come back to its original shape, right? The final length that it has is original. So what I'm basically saying is that the extension that we provide is reversible, okay? All right, all that is fine. So I'm going to keep doing this. So you'll find that till you reach a point, let's say somewhere, let's call it A on the graph. Till you reach a point A, this proportionality is valid. But what happens is, if I increase the stress beyond that point, the strain that I produce is actually much greater. It's no longer proportional. Okay. So what basically means is that so till before that point A, the same stress produced some sort of strain, right? But after that point, for the same increase in stress, the increase in strain is greater, or rather, the slope of the graph will basically reduce. So this is what happens. So that point A, till where the proportionality is valid, is called the proportionality limit. Okay, and beyond that, there is no more proportionality. Okay, so that happens. But even though the proportionality is not valid, if I bring it back, right? If I reduce the force slowly, it will still come back to its original length. So it is still completely elastic, even though the proportionality is not valid. Okay, fine. But next comes, let's say I'll take another point B. Okay, so after that point B, now that I've increased the stress beyond that point B, now if I bring it back slowly, what I find is at zero stress, there is a net strain, there is a net elongation. In other words, we've created a permanent deformation, a permanent elongation. So that point B is called the yield point or the elastic limit. So that basically means that if I produce a stress beyond that point B, if I bring it back slowly, I will end up making a permanent deformation or a permanent elongation. Now that point, as I said, is called the yield point, and the stress associated with that point is called the yield stress. Now what happens beyond that? What happens if I increase the stress beyond that? So what we find is, so till the graph reaches a point C, the strain for a corresponding increase in stress is very large. So basically, even for a small force, the elongation produced is very large. So the slope of the graph from B to C is very less, it's very small. So that's what happens. And then from C onwards, that is, if I increase the stress beyond C, then the slope basically increases. So the strain produced is not as much as compared to the previous case. But yeah, so the slope increases like that, okay, till it reaches a point D, which is the maximum stress possible. It's basically called the ultimate tensile strength. So basically, we've reached a point where the wire is almost going to fracture, almost going to break apart. So at that point, when you increase the stress even further, I mean, you don't even have to increase the stress further to increase the extension or increase the strain. So what happens is the curve goes down. That basically means that even if you reduce the stress beyond that point, the elongation will increase, right? If you reduce the stress, the strain will increase. So that's what that conveys. And finally, we reach a point E, which is called the fracture point, where the wire finally gives way and breaks up. So let me just explain that graph again a little slowly. So we have a wire for which you're increasing the stress, right? So if you see the graph, so till it reaches a point A, which we call the proportionality limit, Hooke's law is still valid. So we find that stress by strain is always a constant, and the slope is equal to the Young's modulus. Simple. Now, but from A to B, stress by strain is no longer it's no longer the same constant. So it is not directly proportional. But till a point B, which we call the yield point or the elastic limit, only till there elasticity is seen. That is, if till I reach the point B, if I stop in between somewhere and I bring it back very slowly, if I reduce the force very slowly, it will come back to its original length. But if I give a stress that's beyond the point B, right, and then if I try to bring it back, it will not reach the original length. It will reach some extra length. So at zero stress also, there'll be some extra length. So you'll end up having a permanent elongation. Okay, so that point B is called the elastic limit. Now then, of course, there is a point C. There's another point C where from B to C, if you go, even for a small increase in stress, there's a very large increase in strain. Right? So for a small force also, large elongation. And then from C onwards, now the slope is increased. It's not that small, it's slightly increased. So even for a slight, it's not, the elongation is not as much as the previous case. So, but from C, we reach a point D. D is basically the maximum stress that this wire can withstand. So it can't go. That's called the ultimate tensile stress. Now, what that means is that beyond D, even if you reduce the stress, even if you reduce the force, the strain will still increase. That is, the elongation will still increase, right? Because it's almost going to break. And then finally, at the point E, can take no more and it will break completely. At that point, the strain is too much and it will break.
For more videos and live lectures on the JEE, click on the sub.
Okay, thank you very much for watching this. Allah Hafiz.